Selectivity is an important aspect, maybe the most important aspect pertaining to tuned amplifiers. It refers to the ability of the amplifier to allow to pick up wanted or desired signal and to reject unwanted signals, undesired signals. It is measured with the help of two parameters. One is skirt selectivity. Skirt selectivity is the ratio of 30 dB bandwidth to 3 dB bandwidth. Another parameter is also there. It is called shape factor. Shape factor is the ratio of 60 dB bandwidth to 6 dB bandwidth. Both are useful to give an indication regarding selectivity of a tuned amplifier. In numbers, another important specification or parameter pertaining to tuned amplifiers is tunability. Tunability refers to ability of the amplifier to stand and function over a specified frequency band. If it is able to stay over the band for longer periods of time, then we say the amplifier's tunability is good. Otherwise, tunability is said to be low or inferior. Tunability's importance lies in the fact that tuned amplifiers are RF amplifiers, high frequency amplifiers, and hence they suffer with the problem of instability, drift. The frequency of operation keep on moving either this way or that way unless proper precautionary steps are taken while designing the amplifier. Tunability gives an indication how far the amplifier is stable as far as its frequency of operation is concerned with respect to time. Multi-stage amplifiers, the second part of tuned amplifiers, a series on semiconductor devices and circuits, lecture number 8.15. Tuned amplifiers are mostly multi-stage amplifiers. They are used as front-end selective circuits in the radio receiver chain. The output of the receiver antenna goes into the tuned amplifiers. There the signal gets amplified. Amplified signal, RF signal, is then given to the remaining part of the receiver, where the information is extracted from the RF signal. This is the second part. In the first part, basic features and fundamental performance indices of tuned amplifiers. They are given. In this session, we focus mainly on different types of couplings that are used in the design of multi-stage amplifiers along with their properties, performance characteristics. Now we move to begin the course session. We consider parallel tuned circuit. By this time, we have already completed part 1. We know the load of the tuned amplifier is parallel tuned circuit or parallel LC circuit. The performance given by the tuned amplifier heavily depends upon the characteristics of tuned circuit. Here, important characteristic parameters of parallel LC circuit is given. Here is shown LC, parallel LC circuit, parallel tuned circuit. Inductor coil is associated always with some resistance, however small it may be. That resistance is indicated by R here. L is inductance of the coil, C is capacitance of the capacitor in the parallel LC circuit. Now, this circuit, it has a certain resonant frequency. That frequency is given by 1 by 2 pi square root of 1 by LC minus R square by L square. Roughly it is 1 by 2 pi root LC. In this expression, R is there, L is there, C is there. All are already defined. Now, there is an expression for RP, LP, CP. What is RP? What is LP? What is CP? This circuit has an equivalent circuit, an equivalent representation. In that equivalent representation, 3 components, 1 resistor, 1 inductor, 1 capacitor. These 3 elements exist. Resistance of the resistor, it is indicated by RP. Inductance of the inductor is indicated by LP. Capacitance of the capacitor in this equivalent circuit is indicated by CP. Here RP is pure resistance, LP is pure inductance, CP is pure capacitance. These 3 components are in parallel. That's why it is called parallel equivalent circuit. The value of RP, value of LP, value of CP, these values can be found in terms of RLC. Those values are given here in the form of expressions. RP is R square plus omega square L square by R. LP is R square plus omega square L square by omega square L. CP is C. The purpose of expressing actual LC parallel circuit in terms of this parallel RLC circuit is, it becomes easy to deal with, to analyze the circuit. This is standard form of a parallel circuit, a standard form involving RLC in parallel. So a lot of information is already available with us. This is the form with which we are already familiar. So once the circuit is converted into this form, so many things can be understood without requiring to do cumbersome calculations. Now Z. another expression is there. Z means impedance of the coil. It is equal to R naught by 1 plus J to Q naught delta. What is R naught? R naught is L by CR. It is in fact equal to Z at resonant frequency. See, Z is impedance. It is dependent upon frequency. Frequency is there inside. Inside this expression, frequency is there. Z is dependent upon frequency. R naught is Z at a resonant frequency. And it can be shown equal to L by CR. Of course, L by CR is equal to Q naught by omega naught C. What is Q naught? Q is omega L by R. Q naught is omega naught L by R. Q naught is Q at resonant frequency. Omega naught is 2 pi F naught, angular resonant frequency. Q naught by omega naught C is R naught or Z naught. It is impedance at resonance. There is delta in the expression of impedance. It is called fractional frequency deviation. What is fractional frequency deviation? Omega minus omega naught by omega naught. Omega is 2 pi f. Omega naught is 2 pi f naught. F naught is resonant frequency. This quantity, fractional frequency deviation. Deviation of the actual frequency from the resonant frequency as fraction of resonant frequency is fractional frequency deviation delta. We come across frequently this quantity in the analysis of these amplifiers. Now, LP, RP, CP are inductance, resistance, capacitance of equivalent parallel RLC circuit. Some more points regarding parallel tuned circuit. Impedance Z is maximum at resonant frequency F naught and falls off shortly for frequencies either below or above resonant frequency F naught. Frequencies F1 and F2 at which relative impedance is 0.707 constitute half power frequencies. In the previous session, we have already seen the impedance of the parallel LC circuit and the gain of the amplifier too. It varies like this. It's a bell curve. At resonant frequency F naught, impedance is maximum. Gain also maximum. At frequencies where relative impedance is 0.707. These are also called half power points or 3 dB points. These frequencies are usually called FL, FH. Here they are designated as F1, F2. The distance between F1 to F2, it is called bandwidth. These frequencies are half power frequencies. Bandwidth and selectivity. As already mentioned, bandwidth is distance between F1 to F2 or F2 minus F1 is bandwidth. It can be shown equal to F naught by Q naught. F naught is already defined, already given in the previous slide. Q naught is omega naught L by R. 2 pi F naught is omega naught. And Q naught is, can be shown, Q naught can be shown. By definition, Q naught is omega naught L by R. Okay. It can be shown equal to F naught by B. B is F2 minus F1. This relation has come from, this one has come from this. Now, Q naught is a measure of selectivity of parallel resonant circuit. Higher the value of Q naught, more selective is the circuit and smaller is 3 dB bandwidth. More selectivity means less bandwidth. This has to be kept in mind. Less bandwidth means more Q. Therefore, more Q means more selectivity. Here is shown the circuit of single tuned Why it is a single tuned? If the amplifier houses carries one tuned circuit, then it is a single tuned circuit, single tuned amplifier. Here is shown a multi-stage, two-stage amplifier. Two stages of a multi-stage amplifier are shown. This is one stage, this is another stage. You concentrate on any one stage, first stage, let us say. How many tuned circuits are there in this amplifier stage? Only one. Only one. Here also only one. In the second stage also only one. That's why single tuned circuit, it is single tuned amplifier. Single tuned capacitance coupled. Output of one stage is coupled to the input of the next stage through a capacitor CB. That's why it is capacitance coupled. Multi-stage, more than one stage is there. That's why multi-stage. Here two stages are shown. Previous to these two stages, there may be some more stages. After these two stages, some more stages may still be there. Anyway, if more than one stage is there, it is called multi-stage amplifier. It is CE amplifier. This is common emitter configuration, that's why CE amplifier. So describing the structure of this amplifier, it is called single tuned because single circuit is there. Capacitance coupled, capacitor is used to couple. Several stages are there, multi-stage amplifier. Configuration is a CE, that's why CE amplifier. It is an important configuration, so some parameters pertaining to this amplifier are given here. Voltage gain of this particular amplifier is given by this expression. AB equal to minus GM RB prime E by RBB prime plus RB prime E RT by 1 plus J 2 QE delta. GM is transistor's parameter, transconductance. RB prime is resistance between internal base and emitter. RBB prime is base resistance. What is RT, what is QE, what is delta, all those things are explained here. Where 1 by RT is equal to 1 by R0 plus 1 by RP plus 1 by RI. RP is R square plus omega square L square by R. RP, what is RP? It is resistance in the equivalent circuit of parallel LC circuit, that part. Then what is R0? R0 is output resistance of current generator GM VB prime E. This current generator is in the equivalent circuit of pi equivalent circuit of BJT. RI is input resistance of next stage. Delta is fractional frequency variation equal to omega minus omega naught by omega naught. This is already defined. So this expression voltage gain is for one stage, for single stage. In the expressions that are given in the previous slide, QE is there. QE stands for effective quality factor of entire output circuit. It is given by omega naught C RT. It can be shown equal to RT by omega naught L. Resonant frequency omega naught. See, in the expression of QE, you can find omega naught. Omega naught is 1 by root L. Resonant frequency. 3 dB bandwidth is B equal to 1 by RTC. To get these expressions, one needs to do analysis. It is not very complex. It is not that much complicated, but it is somewhat laborious. Here we have not undertaken the analysis. We are limiting ourselves only in giving you the results of the analysis. Another circuit, amplifier circuit is shown. tapped. Here is a tap. Here is a tap. Tapped. Single tuned. Single tuned means single LC circuit in each amplifier stage. See, here is one tuned circuit. Here is one tuned circuit. Two stages are shown. In each stage, one tuned circuit is there. Therefore, single tuned. Capacitance coupled. Why it is capacitance coupled? Here is a capacitor. This capacitor is to couple output of previous stage to the input of next stage. So RC coupling is used. That's why it is capacitance coupled amplifier. It is also CE. One can see it is CE configuration. Hence the name tapped single tuned capacitance coupled amplifier. Now, in a multi-stage tuned CE amplifier, the output impedance of each stage is high, while the input impedance is low. See, there is a serious disadvantage, shortcoming with BJT amplifiers, that is low input impedance. Here also, these stages face that problem, that shortcoming exists here too. For impedance matching and consequent maximum power transfer, very often the tuned circuit coil is tapped, resulting in a tapped single tuned capacitance coupled amplifier. So here is one stage with output impedance high. Here is next stage with input impedance low. If we provide connection without adjusting their impedance levels to certain equality, certain same level, mismatch comes into being and the output of a stage cannot go completely into the input of the next stage. Reflections happen. To avoid this situation, to see that output of one stage goes completely into the input of next stage, certain kind of matching has to be performed here. In the present case, matching is done through tapping. So the purpose of tapping is to provide impedance match between output of one stage with the input of next stage. Another configuration, inductively coupled single tuned CE amplifier. Here two stages are shown, both the stages Q1, Q2. They are in CE configuration, that's why it is labeled as CE amplifier. Single tuned, reason is you can find only one tuned circuit in each stage. Here one tuned circuit, here another tuned circuit. That's why it is a single tuned, inductive coupled. A transformer is used to couple the output of one stage to the input of the next stage or to the next stage. Transformer. That's why inductive coupled. Now, the coil L of the tuned circuit is inductively coupled to coil L2, feeding the next stage. The resistance combination R1, R2 along with RECZ provides necessary bias. Parallel tuned LC circuit is set to resonate at the input signal frequency. See, this is one LC circuit, this is another LC circuit. All these circuits, they are set to resonate at a frequency which is equal to input frequency. Of course, that is synchronous tuning. Another amplifier circuit, double tuned. So far, we considered single tuned amplifier circuits, now double tuned. It means in each stage you find two LC circuits. So double tuned transistor amplifier. Here is a circuit. You can find two stages are shown. This is one stage, this is another stage. In each stage, you can find two tuned circuits. This is one tuned circuit, this is another tuned circuit. In the second stage, this is one tuned circuit, this is another tuned circuit. So it employs two tuned circuits in each stage. That's why it is called a double tuned amplifier. It is transistor amplifier. Okay. CE configuration is used in each stage, so it is CE, double tuned CE amplifier. Now a few points regarding its functionality and its description. It uses load impedance in the form of two tuned circuits coupled inductively. See, coupling is inductive. It is pointed out that both the tuned circuits are tuned to the same frequency, namely signal frequency. So two tuned circuits are there and both these two are tuned to signal frequency. Note that the double in the name of this circuit refers to number of tuned circuits, not the number of tuned frequencies. So all are tuned to one frequency of the signal. Now a few points, features of a double tuned transistor amplifier. The gain of double tuned amplifier is nearly same as that of single tuned amplifier. It provides larger 3 dB bandwidth than single stage and hence larger gain bandwidth product. It provides a gain versus frequency curve having a steep sides and a flatter top, which is an advantage. However, it suffers with a disadvantage of difficulty of alignment. The alignment of double tuned amplifiers is problem and hence we go for stagger tuned amplifiers. So first point is that double tuned amplifiers provides more gain than single tuned amplifier. Second point is double tuned amplifiers provide more 3 dB bandwidth than a single stage and hence larger gain bandwidth product is possible. Its gain frequency characteristic, third point says, is a better one. These are all plus points. When it comes to shortcomings, there is a difficulty in the alignment process. Double tuned amplifier houses two LC circuits, parallel LC circuits, and tuning both the circuits to one frequency and maintaining them at one frequency is a serious problem, a serious complication. Because of this difficulty, people tend to prefer stagger tuning. Some more points regarding double tuned transistor amplifiers. 3 dB bandwidth is given by omega naught by q square root of b square minus 1 plus or minus 2b. For practical amplifiers, b value is in between 1 and 1.7. From this expression, we can say that double tuned amplifier has more bandwidth than single tuned one. For single tuned one, it is omega naught by q. With the increase in the value of B, not only bandwidth but also overshoot increases, which is an inconvenience, a disadvantage, a harmful consequence. Now, a few points regarding cascading, effect of cascading. What is cascading? If we give output of one stage as input to the next stage, then we say these two stages are cascaded. Their connection is a cascade. When we cascade two amplifiers, what happens? How this connection affects gain, how it affects bandwidth, those issues we consider here. In case of identical single tuned cascaded sections, the bandwidth can be expressed in terms of bandwidth of single stage B1 as. For n stage, bandwidth is B1, bandwidth for single stage multiplied by 2 power 1 by n minus 1 under square root or half. Cascading has the deleterious effect, harmful effect of reduction in 3 dB bandwidth of amplifier. This is from this expression. However, this fall can offset to some extent by reducing the Q of tuned circuit. Notice, for communications, amplifiers bandwidth is as important as gain. Both are important. So cascading here, it is reducing the bandwidth, but of course this reduction can be to some extent arrested by reducing Q of the tuned circuit. In case of composite amplifier with double tuned cascaded sections, bandwidth is given by B2N is B2 cascaded, double tuned cascaded section, individual section bandwidth. It is multiplying with 2 power 1 by n minus 1 power 1 by 4. Here B2 is bandwidth of double tuned single stage, B2N is bandwidth of n identical stage double tuned cascade amplifier. With this, we come to the end of part 2 on tuned amplifiers. In this session, we introduced various types of coupling mechanisms that are used in the design of multi-stage tuned amplifiers. Hope this session is useful to you. We meet again in another session with a new topic soon.